Yes, thank you for the introduction and good morning, everyone, again. Even though it's night here, it's 1 a.m. here in the Netherlands. So, yeah, but welcome. And indeed, I'll present my paper on Penrec, a hybrid recommender system for pension savings. And first, let's talk about the motivation. Why? Why should I work on this pension recommender system? First, there are more and more people that are becoming self-employed, freelancers, and they typically on the save. They do not have occupational pensions once they retire, and they are at risk of not being able to maintain their lifestyles once they retire. So there's significant retirement risks for this set of people and even people that just want to maintain a specific lifestyle, even if they are employees after they retire, they could, use some sort of a recommender system that could help them make personalized recommendations to maintain the lifestyle. Another thing is information overload for self-employed again. There's a lot of pension products and diverse schemes that exist for the individual to select from, but oftentimes this is a bit of an overload, and this can lead to decision paralysis and suboptimal savings choices. And third motivation is that there's no power work that exists that I found in the literature that apply deep learning based recommender systems for the pension domains in particular and applying or using behavioral measures as features. So most, if you find work, they often just use normal socioeconomic or biographic data as the features that they use to train a recommender system. So first, let me go into a slight evolution of recommender systems. So by early 90s, 1992, it started for more information retrieval mechanisms, information filtering, Belkin and Croft, and then little collaborative filtering that use, similarities between either users or items that are meant to be recommended that try to make a recommendation based on these kind of similarities started coming up. And then by 1996, some companies already started trying to implement these algorithms on a more commercial level to try to make use of this technology. And by 2006, the Netflix prize, which was very common, so ubiquitous that a lot of people know about, that used matrix factorization models and collaborative filtering also to make the Netflix recommendation, also based on user similarities. And then, yeah, by the 2010s, it was more factorization machines and yeah, different versions of factorization machines that became very popular then. And by the time we got to 2016, then it was more, okay, people started mixing it a bit more, hybrid models with some deep learning or because then deep neural networks were still gaining popularity, but it hasn't been as widespread as it is now. And by the 2020s, it was more transformers, which is also the technology behind LLMs and so on. That was the state of the art. So if I'm to summarize this, so it's you can see it started as just basic data mining technology, data mining information retrieval techniques, statistical forecasting theories that were just applied to make some sort of personalized suggestions, and then it's filtered into content-based filtering that tries to compute similarities between item features and user preference profiles using things like weighted vector representations to and detailed feature descriptions of items to make recommendations. Then it was collaborative filtering that predicts by leveraging behavioral patterns of similar users. This person is similar to you, likes this thing, maybe you will like it. That and it can be implemented via memory-based nearest neighbor methods or model-based machine learning algorithms. And then hybrid techniques, ensemble techniques that combine multiple recommendation methods to potentially limit some of the limitations and weaknesses of individual methods. Based on my literature review, the hierarchy is, as I said, content-based collaborative filtering hybrid. And then collaborative filtering can be further subdivided into model-based filtering techniques and memory-based filtering techniques, which can further be subdivided in the memory-based filtering techniques into item-based approach, user-based approach, and case-based approach. And the model-based techniques uses the general machine learning techniques that exist, clustering approaches, Bayesian networks, reinforcement learning, multi-layer perception, etc., etc. So in my own work, I used memory-based filtering technique and then model-based filtering technique and combined it into an hybrid recommender system, but we will get there. So if I'm to explain some of the basic concepts behind this, the model, the techniques that I've mentioned. So if you think about item hierarchy technique, it's something like you bought a bat, you might also need a ball because, bat and ball go together in a mental mind, mental space. Or if it's something like attribute based, then it's that you like action films that the star Clint Eastwood, for instance, and therefore you might like a movie that he has starred in, which is like Hogan's Bluff, for instance. So it's specific attributes. You meet that attribute requirement, you get recommended. You get a recommendation based on that. And then collaborative filtering based on user similarity is that, someone that is similar to you, someone that has the same characteristics or attribute as me, for instance, likes Coke or pizza, then maybe I also, would like Coke or pizza. And if it's based on the item and not the user, then it's that the thing itself, like, Superman, you like Superman, and then you would likely like Spider-Man because Superman and Spider-Man are both superhero movies, something like that. And then there are other things like social and choice-based graph, you look at people's friends, people's connections, and say they already subscribe to such a thing, therefore you want to recommend them the same item. And then, model-based method, as I said, that applies, support vector machines, LDA, neural networks, logistic regression, and so on and so forth, that defines a specific output that to be trained upon because it's supervised learning. So you define what you want to learn, which is, say, the item or the movie, what the item is that needs to be recommended. You have existing training data that has the items that people already like. And then you learn a model based on that, and then you plug in any new individual into that model. It makes suggestion based on the generalized model that was learned from the training data. So moving on to my research objectives that I defined for my work. So it's to build a proof of concept, this design, develop a novel deep learning based hybrid, recommender system for personalized pension savings based on user characteristics. And also study the impact of including behavioral measures, particularly risk preferences that was estimated through incentivized experiments and features for improved recommendation to see if we include some of these measures that come from behavioral economics. If we include them as features, do they add value? Do they improve the recommendation that we get or not? Then methodology analysis, I have these two different models, the collaborative filtering techniques that I use, a KNN model and neural networks model, to make a comparison and see how well they do. and then make some sort of evaluation of my recommendation quality against established baseline, combining, demographic data, socioeconomic data, and behavioral features from the Dutch population. Thinking about the general overview of how the the flow chart. So you start from like, data acquisition, in my case, comes from, the Statistics Netherlands and from this behavioral measure from another PhD student. Then you do some sort of pre-processing, fix out, missing data, standard machine learning technique, standard pipeline for machine learning techniques in general. Then you make model selection and training. So based on some sort of parameter tuning, hyperparameter tuning methodology, you make the selection of the best models that fit the research question. And then you do some sort of evaluation and monitoring, then deployment, recommendation generation, and serving to feedback and continuous improvements back to gathering data from based on the feedback, and then the cycle continues for continuous integration and continuous development of the system. So this is how I imagine it. In my case, as I said, I settled on applying KNN collaborative filtering, which is a traditional nearest neighbor method using maximum inner product search on similarity metrics. So, and categorical features were one-hot encoded, numerical features were concise to 20 bins and normalized. And then there's deep learning architecture on the other hand, which had 3 hidden layers. So with first hidden layer having 128 nodes, 64, 32, some sort of dimensionality reduction. And then the output is a similarity matrix as well, such that it can fit with the collaborative filtering. We use contrastive learning to cluster similar users in an embedding space and try to find similarity based on that. Embedding dimension enables efficient approximate nearest neighbor search, and then users with similar attributes can be pulled together while dissimilar users can be pushed apart. And then finally, because both the collaborative feature and the deep learning architecture have the same kind of similarity metrics as an output, it makes it a bit easier to make some sort of weighted combination, make some sort of weight on on the final hybrid recommender system itself. So we can just, do some sort of weighted averages of both approaches. And depending on the weight that was assigned to either the first model, the current KNN collaborative filtering, or the deep learning architecture, you get a kind of balance between interpretability and robustness. At least that was the hypothesis, which turned out to be true, of course. So if this image shows everything as the methodology, and because the picture speaks louder than 1,000 words. So as you can see, data goes to data processing, then compute similarity metrics, use k-nearest neighbor using and MIPS. The other one is embedding using deep learning, and then uses fast approximate nearest neighbor to obtain a recommendation. And then weighted averages combines the two results into a specific recommendation. So let me talk a bit about MIPS, the maximum inner product search. What was done here is that considering a similarity matrix of individual and features, items, in this case, so the users are n, and each exists in the real number dimension. And then for each user in the D dimension of the feature space, we compute the highest inner product between every individual, every observant. So which is the argmax of the query and the user, essentially. So first step is to find similarity scores between users and other users, sort and choose the top k nearest neighbors of the users, and take the mean of these top k neighbors as the predicted recommendation. For the neural networks methodology, you have all the inputs, which is the features. So all features act as the input layer. They feed into hidden layer. In my case, 3 hidden layers. So first to 128 nodes, hidden layer, then dimensionality reduction to 64, then dimensionality reduction to 32. And then this outputs a similarity matrix, which is actually 40 based on my hyperparameter tuning. So if you imagine this architecture, it's a typical transformer method of neural networks using fully connected neural networks, of course. I varied the embedding dimensions, the hidden layers, and selection of the batch normalization, selection of the activation function, the epochs, the number of epochs, the learning rate drop out. And my multi-similarity loss function applies the employee group, which is employed or self-employed, as the target variable within the similarity matrix, with the same dimensions as the KNN collaborative filtering recommender. So, and the reason I did that was to not bias the output using the using the pension contribution that exists in the behavioral data itself, because I wanted to learn similarities between users, and I just don't want the network to try to learn just or memorize the pension contribution. So my data looks like 66 total features, so 22 categorical features and 44 numerical features, covering financial data, so income, wealth, debt, demographic data, marriage, occupation, education, and behavioral measure, which is a predicted risk preference for the general population. The the first set that I mentioned, apart from the behavioral measure, comes from the Statistics Netherlands. So, and then the behavioral measures comes from a survey that was done by another PhD student that conducted 2 waves of online surveys between May and June 2020 with 18,000 employees and 18,000 self-employed in the Netherlands, randomly selected. And then risk preference was measured through incentivized economic experiment using Statistics Netherlands. In the Statistics Netherlands data that I worked with, there were 9 million individuals, administrative records that I had, and I used heuristic feature selection, Pearson's correlation, to eliminate the 10 redundant features first, and then missing data was handled. 55% in particular was missing in the pension contributions, and I replaced it with 0 value. And such that I was able to retain 99% of the data that I had. Then I selected my test set size as 100,000. So, and all were selected from people that actually had non-zero values for their pension contributions from the administrative record, stratified on employed, self-employed, director shareholders, and benefits recipients categories. For my target, I had the first primary baseline of 10% of gross income. This is motivated by life cycle consumption smoothing theories. And it also sits between 8 to 15% of median earners. And it aligns with international pension policy benchmarks and serves as a behavioral plausible anchor for assessing heterogeneity between and across population. So I thought, okay, we pick 10% of gross income of people and use that as a baseline to compare the recommendation that my system provides as one. The second baseline is the actual pension savings that I mentioned that exist in the administrative data. It's just that, as I said, 55% were missing. So yeah. So we use real pension funds from the administrative record, such that we can reflect the observed saving behaviors of actual individuals. And then we use cross-validation, so tenfold cross-validation for hyperparameter tuning, all those things I mentioned in the deep neural networks, like the dropout and so on and so forth. I used cross-validation to select from a range of values over every of the hyperparameters. And then my experiment was run on a shared cluster of 500 gigabyte RAM, 16 core Intel Xenon. And I used key libraries like Polars because I was working with large data, ScanNN to do vector similarity search, and TensorFlow similarity for scalable neural network training. Now, applying KNN on on my data, cross-validation identified a number of neighbors of 25 as being the optimal number of neighbors to balance, robustness to outliers and avoid overcompensation for high income earners. And what I noticed was that on average, employees had, value of like, 7,908 as seen in the table. And on average, the actual pension save is like 6,735. And my recommendation for the KNN recommender engine, the first one, with the one with the uses MIPS, was about 7,149 for the employees. And what this means is that, well, about 759 euros below the income value has been recommended on average. So taking all the test sets on average. And then about 414 above the actual savings. So this lies somewhere in between. And I, empirically deem this as being plausible. The same for the self-employed. So even though this is actually a bit higher in terms of the amount that is recommended, it's higher than both the base and the actual pensions, which confirms on the saving for my perspective. And then we recommend them to save a bit more. And for the director shareholders, these are people that own, shares in major companies and big companies. They already have high values, high income baselines, and and actual pensions. So it under recommends to them the amount that the recommender recommends to them to save. So it's about 5,000 below the baseline. And this is likely also potentially due to organizational assets that they have potentially. And for the benefits recipients, so people that are under, unemployment benefits or disability benefits, in this case as well, the recommendation lies somewhere in between the 10% income baseline and the actual pensions. And I noticed the limitation for the KNN recommender was that selected neighbors, the K25, often are neighbors that predominantly share identical education category, employment type, province, income status, and yeah. So this reduces recommendation diversity because it strictly selects from people that have these similar categories with other users. Doing the same analysis for the deep learning recommender system, my optimal configuration for that was embedding dimension of 40. So, and the hidden layers I mentioned before, the batch normalization and leaky ReLU activation selected, and 40 epochs for the number of times that the model makes a pass through. Learning rate of 5, 8, yeah, 5 times 10 to the minus 6, and then dropout of 0.3. And as I said, multi-similarity loss function applied to the employee group as a target variable. And what I observe, keeping the baselines as they are, is that now the recommendation from that's meant to be deep learning recommendation. It's not KNN recommendation. Yep. Yeah, so we now get 75% closer to the actual amount that people save in the data as compared to KNN in terms of the recommendation. And this is using the employee group as the target variable and not the actual pension savings. So by nature of the deep learning recommender system itself, it trails slightly more towards the actual pension savings that exist in the data. For the self-employed as well, it still encourage them to save, but yeah, it's now slightly in between the baseline in terms of the average recommendation, in between the baseline and the actual pension that exists in the data. The director shareholders maintain the same idea, but just slightly lower amount as compared to the KNN recommendation, but it is very much significantly lower than the baselines. And for the benefit recipient as well, it still lies in between the 10% baseline and the actual pensions. And so my key takeaway from that was that the neural networks I observed select more diverse neighbors. So you can find an employed that is similar to a self-employed, or you can find a self-employed that is similar to employed people. And this adds more robustness in terms of the selection and diversity of neighbors that exist across categorical variables. For instance, overcoming the rigid categorical matching limitation from the KNN recommender system. So as I said, from the cooperative analysis, so the deep learning recommendation 75% closer to the actual pension baseline than KNN for the employee group. Both models generate recommendations within the reasonable baseline ranges, validating the effectiveness of the framework, at least empirically. Traditional KNN has higher interpretability because clearly you can say it's because of these specific categories that match strongly. That is why the recommender system made the recommendation, and it's very easy to find this out because you but the deep learning has higher robustness. It can capture more nonlinear relationship, and it has more flexibility in terms of similarity across categories, but it is black box and you cannot make any explanation of why the model makes suggestions. So KNN neighbors share identical education, province, employee type, and deep learning includes diverse individuals across categorical variables. Then the impact of the behavioral features in on the models. So when we include risk preference as a behavioral feature, on average, it's in general reduces the average recommender differences by about 100 euros across all employment groups. And also including this improves the similarity error from 1.38 to 1.35 when we include the behavioral feature variable. Also, recommendation volatility significantly reduced, which is evidenced in the paper by a smoother nearest neighbor plot of individuals. I have this in my appendix, also in just a sample of how this plot looks like for the nearest neighbors. And then as such, the empirical analysis also supported that including behavioral measures does add meaningful value, albeit marginal, but it adds value beyond demographic and financial data alone for pension recommendation quality. Yeah, so in conclusion, we made a novel implementation of deep learning hybrid architecture for pension domains. For the pension domain, combining KNN collaborative filtering with deep neural networks using contrastive learning, and homogeneous output design allows for easy integration and creation of the hybrid model. Deep learning captures the diverse user similarities beyond rigid categorical matching, providing recommendations that are 75% closer to actual pension savings than the KNN recommender engine. And then rich preference as a behavioral feature marginally but meaningfully improves recommendation across all employment groups. And weighted combination approach successfully balances, interpretability, complexity, and robustness trade-off. And in the future, we could still incorporate, multimodal data extension, incorporating like text and images in there. Additional behavioral measures like time preferences, financial literacy, ambiguity, and so on. Online deployment of the application with human in the loop validation that can observe the that can observe the recommendation and give feedback based on the life cycle that I showed before. This would be also very, very useful in my opinion. And then can try some more LLM based recommendation and also incorporate it and see how it differs from just general deep learning recommender engine. And I think that this can be a practical application for the pension advisory that can, provide explainable similar user justifications and provide, transparency and trust for why certain, recommendations has been made. And some references for my talk. And yeah, thank you. Yeah.
It's a great presentation, Doctor. And does anyone have any question?
Questions.
Are there any questions from forum? The article is well written and the experiment results are great. It's well presented. It's a remarkable article and research work.
Thank you.
I have some question.
Yes, please.
How did you prevent overfitting in the deep learning model? That is one.
Sorry, please, can you repeat that? How did
you prevent overfitting in the...
How did I permit a fit?
Yep.
Okay.
That is one. And
okay.
You combined collaborative filtering with deep learning.
Yes.
Why did you combine? Instead of choosing one, you can choose one, and if you can explain, it will be great. Thank you.
Yes. So I can go a bit into that. So the idea for the first question, selecting fitting for the neural networks is embedding the features or all the things that I gathered from the Statistics Netherlands. So these are things like people's financial information, their biographic data, including this behavioral data. They are all, you can imagine them as column in a table, right? They are the features. And then I make an embedding, which is just a vector space representation, number representation, Cartesian representation of this values to identify individuals that are similar to one another. So you can imagine them as a 66-dimensional plot. Of course, we cannot imagine more than 3D as humans, but it can put every individual a point in 66 dimension. And then by looking at distance between individuals, I can select neighbors. And these neighbors are now what are used to make recommendation that, okay, this person is close to you in that 66-dimensional plot, then this person also can save the amount that you save, for instance. And so this is what does the fitting. We do an embedding using the neural networks does the embedding in a vector dimension, and then we can find distances, Cartesian distances between people. For the second question, the reason I combined two different methodologies like this is I wanted to interpretability was very important to the domain experts. So when I spoke to people from the pensions industry and I was telling them about my work, they were like, okay, these are nice methodologies, but we really often like to know why these models make some of these predictions, because there are a lot of risk involved. Even as a decision assistant mechanism, we want to know some reason why. But some people are just interested in, the best results, which is the deep learning model. As I said, the first model can easily give an explanation. This person has similar province, lives, has the same similar amount saved, similar age, for instance, and say this is why the recommendation was made. But the second model will not necessarily select people that have those similar attributes. It can select over some nonlinear relationship that exists. Therefore, in my weighted averages, people that are very much interested in explainability, interpretability, they're going to shift a very high weight to the first model. So maybe like 0.9 weight and 0.1 for the neural networks. And so the recommendation, they can with a high confidence say, based on the categories from the KNN method, the recommendation was made. But people that are not interested in that interpretability, they shift the weight a lot more on the deep neural networks, which is maybe 0.9 there, and then 0.1 for the KNN, and then they just say we have the best result that we can find for you. So that was the idea behind selecting and combining multiple methods. And as I
Yeah,
said at the beginning as well, hybrid methodologies tend to just try to mitigate limitation of one for the other. So the more you combine ensemble models, the more you can mitigate the individual limitations that some of these models are. So in
yeah,
a way, you average out the limitations of models. So in general, we tend to use ensemble model and machine learning, a lot of machine learning applications. Yeah.
yeah, yeah. Thank you. That's great. That's great. Thank you very much.
Yes. Thank you. And thank
Does
you.
any
Thank you for your questions and listening to all I have to say.
Can I
That's great.
ask
Thank
a
you.
short question?
Yes, please.
Because I think it's a very exciting and very hot topic. Pension system are shifting responsibility from employers and governments to individuals, but most people lack of knowledge, this knowledge about it.
Yes.
And I think it's a very important question in the EU. I am from Hungary. It is
Ah,
also
nice.
almost 2 o'clock now in the evening.
Yes.
So I would like to see clearly if a kind of scalable AI system can provide such guidance for millions of citizens at the low cost, making pension planning more accessible, more accurate, and more aligned. What do you think about this, and what do you think about the human behavior patterns? How you can count with it in your research?
Yes. So on the highest level, I believe with a lot of agents that exist this way these days, as I said in my future works with LLMs and so on. So using agents, using large language model agents, you can now add some more explainability, annotation, and even more explanation, that is more user-friendly to some of the results that can be attained from this kind of systems, recommender systems in general. So you include, the all the data that were used and the annotation that exists about them. You include them as, as a document, and then the LLM can make a summarization and make proper story about the the recommendation, for instance. So I think this is very possible, but as you said, with people, oftentimes the reason why I think this can only be some sort of assistant, and it cannot be like a financial advisor, for instance, direct financial advisor, is that we always need someone to take on the risk when things go wrong. So if things go wrong, so you suggest someone to save, and maybe some black swan event happens, COVID happens, whatever, and then they still lose all their pension despite using some of this system. Then it becomes hard to say, okay, but there's the system that did it. So there still needs to be people that would be in charge and that would take on the risk, that would take on the additional burden of when things go wrong, you know. So that's why in my opinion, it should be a decision-assisted system, and it shouldn't exist as, you know, the system that everyone uses for whatever they are, you know, whatever they want to save. You know, it shouldn't be just deployed straight to the user and just say, hey, this is how you select your savings. This is my opinion on this. I hope it answers your question a bit.